Imagine a car moving along a road. We can track its position over time. After a few seconds, it's traveled a certain distance. If I told you it traveled 60 miles in 1 hour, you could easily tell me its average speed, 60 miles per hour. That's simple division. But what if I asked you a much harder question? Not its average speed over an hour, but its exact, instantaneous speed at a single moment in time, the speed on the speedometer, right now. How do we even begin to calculate that? This question, the problem of finding an instantaneous rate of change, is the first great problem of calculus. To tackle this, let's visualize the car's journey on a graph. Let's say the horizontal axis represents time, and the vertical axis represents the car's position. The path of its journey might look something like this curve. Calculating the average speed between two different moments in time is straightforward. We just pick 2 points on this curve. The average speed is simply the change in position divided by the change in time. Geometrically, this is the rise over run, which you might recognize as the slope of the line connecting those 2 points. This is called a secant line. But we want the speed at a ** instant. That corresponds to a ** point on our graph. How can you find the slope of a single point? You can't. A slope requires 2 points, so let's try a trick. Let's take our 2 points and move them incredibly close together. Watch what happens to the secant line as the time interval between the points delta x gets smaller and smaller and smaller. The line pivots and seems to settle into a unique final position, just kissing the curve at that single point. This unique line is called the tangent line. Its slope represents the instantaneous speed at that exact moment. But how do we find *its slope? We are asking what happens to our slope formula as the change in x, delta x, approaches 0. This is the idea of a *limit*. This is the core question of what we call differential calculus *. Now, for the second great problem. Suppose we have a shape defined by some arbitrary, complicated curve, not a simple rectangle or circle, but the area underneath this curve, between 2 points. There's no simple geometric formula for this, so how could we find it? Well, we could try to approximate it. We can fill the space with simple shapes we know how to measure, like rectangles. This is a decent estimate, but it's not perfect. You can see the gaps and the parts that stick out. It's clearly inexact. How can we get a better approximation? We can use more rectangles and make them much thinner. That's much better. The error is smaller. And this leads to the key idea. What if we could use an infinite number of rectangles, each one being infinitesimally thin? In the limit, as the width of these rectangles approaches 0, their sum will perfectly match the true area. This process of summing up infinite, tiny pieces to find a whole is the core idea behind the second branch of calculus. To represent this infinite sum, we use a special symbol, the integral. This is the heart of integral calculus *. So here they are, the two great problems that drove the invention of calculus. On one side, the tangent problem, finding the instantaneous rate of change, and on the other, the area problem, finding the total accumulation under a curve. They might seem unrelated at first glance. One is about slope, the other about area. But as we'll discover, they are deeply, beautifully connected. They are two sides of the same coin. Understanding this connection is the key to understanding calculus. In the last part, we were left with two seemingly impossible problems. How do we find the exact slope of a curve at a single point when slope requires 2 points? And how do we find the exact area under a curve when our formulas are for straight-sided shapes? The answer to both lies in a single, powerful idea, an idea that philosophers have wrestled with for millennia, the concept of infinity. To build our intuition, let's consider a famous ancient puzzle, Zeno's paradox. Imagine the great hero Achilles is in a race with a tortoise. Achilles is a fast runner, but to make it fair, he gives the tortoise a head start. Let's say the tortoise starts at position 1 and Achilles starts at 0. Now, the race begins. In the time it takes Achilles to reach the tortoise's starting position, the tortoise has moved a little bit ahead. So Achilles must then run to that new spot. But in that time, the tortoise has moved ahead again, just a tiny bit. This process repeats. Achilles covers half the remaining distance, and the tortoise crawls ahead yet again. Logically, it seems Achilles must perform an infinite number of tasks to catch the tortoise. And common sense balks at this. How can you complete an infinite number of steps? It seems he can never catch up. This is the paradox. But let's look at it mathematically. What is the total distance Achilles is running? First, he runs a distance of 1/2, then a quarter, then an eighth, a 16th, and so on forever. We are adding an infinite number of terms together. For centuries, this was a profound puzzle. But calculus gives us the tools to see the answer clearly. Even though there are infinite terms in this sum, the total sum itself is not infinite. It adds up exactly to 1. The infinite series converges to a finite value. Achilles does catch the tortoise, and he does it at the 1-meter mark. This is the conceptual breakthrough we need. It's the key that unlocks calculus. We can handle an infinite process and arrive at a single, exact, finite answer. So, how does this help us with our two great problems? On the left, we have our tangent problem. We can't calculate the slope at one point, but we can approximate it with a secant line connecting two nearby points. Watch. As we slide the second point infinitely close to the first, our approximation gets better and better. We are creating an infinite sequence of better approximations, just like Achilles taking an infinite number of steps. We are homing in on the exact answer. Now, look at the right. We have our area problem. We can't calculate the curved area directly, but we can approximate it by filling it with simple rectangles that we can measure. It's a crude approximation at first, but what if we use more, thinner rectangles? The approximation gets better. The error gets smaller. And if we use even more, infinitely thin rectangles, you see the profound connection. Both problems, which seemed so different, are solved with the exact same master strategy. It's the engine of calculus. We start with an approximation we can calculate. We then systematically refine that approximation, pushing it through an infinite process. And finally, we use the tools of calculus to find the exact value that this infinite process leads to. We take the limit. This strategy, approximate, refine, and take the limit, is what we will explore in detail next. It is the heart of everything we are about to learn. In our last discussion, we developed an intuition for approaching a point on a function. We saw that even if we can't land exactly on a value, we can get incredibly close to it and observe where the function is heading. Now, in scene 3, let's make this idea more concrete and powerful. Consider this function. F of x equals x squared minus 1, all divided by x minus 1. Let's see what its graph looks like. It appears to be a simple straight line. But there's a catch. What happens if we try to plug x equals 1 directly into our function? We get 1 minus 1 in the denominator, which is 0. We can't divide by 0, so the function is technically undefined at x equals 1. The graph has a hole. It's a single point that's missing. And this presents us with a fascinating question. Even though the function isn't defined at x equals 1, can we talk about the value at should asterisk have there? What value is the function zeroing in on as we get infinitely close to 1? Let's investigate numerically, just as we did before. We'll build a table of values and sneak up on x equals 1 from both sides. Let's start with an x value a little less than 1, say 0, 9. Our function's output is 1, 9. Now, from the other side at 1, 1, the output is 2, 1. Okay, let's get closer. How about 0, 99? The output is 199. And at 1, 0, 1, it's 2, 0, 1. I think you see the pattern. If we get even closer, say 0, 999, and 1, 0, 0, 1, the outputs are 1, 999 and 2, 0, 0, 1. It seems undeniable that the closer x gets to 1, the closer the function's value f(x) gets to 2. This value 2 is what we call the limit. This concept is so fundamental to all of calculus that it has its own precise mathematical notation. We write it like this. We say, the limit, as x approaches 1, of our function is equal to 2. But getting closer still feels a bit vague. To make calculus rigorous, mathematicians needed a waterproof definition. This led to one of the most brilliant ideas in mathematics, often called the epsilon delta definition. It sounds intimidating, but the core idea is simple. Think of it as a promise. The limit, L, is the value we claim our function approaches. The promise is this: you can challenge me by defining a tiny tolerance range around that limit. You tell me, I want the function's output to be within this specific distance of 2. We'll call that small distance epsilon. So you want the function's value to be trapped between L minus epsilon and L plus epsilon. That's your challenge. My part of the promise is to respond by finding a corresponding range around our input value, c equals 1, such that for any x I pick inside this new range, I can guarantee the function's output will land inside your epsilon tolerance zone. We call the size of my input range delta. The existence of the limit is the guarantee that I can always win this game. No matter how demanding you are, no matter how small you make your epsilon challenge, I can always find a delta, a small corridor around x equals 1 that satisfies your request. Watch. As your epsilon tolerance gets smaller, my delta corridor must also get smaller, but one always exists. This dynamic relationship is the heart of the limit. It's a formal promise that we can get not just very close, but arbitrarily close to our limit value. And it's this rigorous idea that turns the intuitive notion of approaching into the solid foundation upon which all of calculus is built. In the next scene, we'll use this concept to explore some rules that make finding limits much faster. In our previous discussion, we established a formal definition for a limit. We saw how it describes a function's behavior as it gets infinitely close to a certain point, even a point where the function itself might be undefined. This idea is more than just a mathematical curiosity. It's the very foundation for one of the most important concepts in all of calculus: continuity. So, what does it mean for a function to be continuous? Intuitively, the idea is wonderfully simple. If you can trace the entire graph of a function with your pen without ever having to lift it off the paper, that function is continuous. There are no gaps, no jumps, no holes. It's a single, unbroken curve. But as mathematicians, we need to move beyond intuition and establish a rigorous, testable definition. This is where limits come directly into play. For a function, let's call it f, x, to be continuous at a specific point, let's call it c, 3 specific conditions must all be met. Let's look at these 3 conditions one by one. First, the function must actually have a value at the point c. You can't have continuity at a location that doesn't exist for the function. There has to be a defined point on the graph. Second, the limit of the function as x approaches c must exist. This means the function must be approaching a single, finite value from both the left and the right side. If the function is heading towards 2 different places, the limit doesn't exist. And third, and this is the crucial step that ties it all together, the value the function is approaching, the limit, must be the same as the function's actual value at that point. The destination must match the location. If any single one of these 3 conditions fails, the function is considered discontinuous at that point. Let's visualize what these failures look like. Here, we have a function that looks perfectly fine, except for this one spot. At the point where x equals c, there's a hole. In this case, our first condition fails. The function's value, fc, is undefined. Even though the limit clearly exists, we can see what value the function is approaching. The lack of a defined point creates a discontinuity. This is often called a removable discontinuity. Now look at this second case. Here, the function's value is defined at c, you can see the solid dot. However, as we approach c from the left, the function heads towards one value. But as we approach from the right, it heads towards a completely different value. Because the left-hand limit and the right-hand limit do not agree, the overall limit does not exist. Condition 2 fails. This is called a jump discontinuity. You would have to lift your pen to get from one piece of the graph to the other. Finally, let's look at this third scenario. Here, the function is defined at c, we have a solid dot, and the limit also exists. The function is clearly approaching the value at this hole as we come from both sides. so conditions 1 and 2 are met. But the problem is that the limit, the value the function should have, is not the same as the value it actually has. The point is misplaced. This violates our third condition. The limit does not equal the function's value. This is another type of removable discontinuity. Okay, now let's bring this back to the function we examined in the last scene. We were looking at the function f x equals x squared minus 1 all over x minus 1. We know this simplifies to the line y equals x plus 1, but with a crucial exception. At x equals 1, the original function is undefined because it results in division by 0. It has a hole. This is a classic example of our first type of discontinuity. Condition 1 fails. f1 is not defined, but the beauty of the limit is that it tells us exactly what value is missing. We calculated that the limit of this function as x approaches 1 is 2. The limit tells us what the function's value should be to make the graph whole. So, we can remove the discontinuity. We can create a new, piecewise function that is identical to our original function everywhere, but we explicitly define the value at x equals 1 to be 2. Watch. By plugging that hole, we have now satisfied all three conditions. f1 is now defined as 2. The limit as x approaches 1 exists and is 2, and the limit now equals the function's value. The function is now continuous at x equals 1. This ability to understand and, when possible, resolve discontinuities is fundamental. Because, as we're about to see, the powerful tool of the derivative can only be used on functions that are continuous. Without continuity, the very idea of an instantaneous rate of change at a point breaks down. In our first scene, we were confronted with the tangent problem, how to find the exact slope of a curve at a single point. We saw that using 2 points and a secant line gave us an approximation. Then, in the last few scenes, we developed a powerful mathematical tool called a limit, designed to analyze what happens as we get infinitely close to something. Now, in scene 5, it's time to bring these two ideas together. We're going to use the precision of limits to solve the tangent problem once and for all. Let's return to our familiar parabola, y equals x squared. But instead of picking specific numbers for our points, let's think more generally. Let's call our first point P. We won't define its x-coordinate as 1 or 2, but simply as x. That means its y-coordinate is the function's value at x, which we write as fx. So P is the point x, fx. Now, for our second point Q, let's place it a small horizontal distance away from P. We'll call that horizontal distance h. So the x-coordinate of Q is x plus h, and its y-coordinate is therefore f. X plus h, the line connecting these 2 points is, as we know, a secant line. Its slope is a good approximation for the tangent slope at P, especially if h is small. But we can do better than an approximation. We can calculate the exact slope of this secant line algebraically. The slope of any line is simply its rise over its run. Let's visualize that on our graph. The run, the horizontal change, is the distance between the x-coordinates. That's x plus h minus x, which is simply h. The rise, the vertical change, is the distance between the y-coordinates. That's f, x plus h minus fx. So let's write this down. The slope of our secant line is rise over run. Now we can substitute the expressions we just found. The rise is f, x plus h, fx, and the run is h. Notice how the colors in the formula match the distances on our graph. This expression, f, x plus h, fx slash h, is incredibly important. It's called the difference quotient and it represents the average rate of change between x and x plus h. This formula gives us the slope of the secant line for any value of h we choose. But we don't want the secant slope, we want the tangent slope. To get that, we need to bring point Q infinitely close to point P. And what does that mean for our formula? It means we need to make the distance h approach 0. Let's watch what happens. As I shrink the value of h, watch the graph. Point Q slides down the curve toward P. The blue line representing h gets shorter, the yellow line representing the rise gets shorter, and most importantly, the green secant line pivots, getting closer and closer to the true tangent line at P. The value of its slope is getting closer and closer to the value we're looking for. we are letting h get arbitrarily, infinitesimally close to zero without ever quite reaching it. This process should sound very familiar. It's a limit. To formalize this, we take our expression for the secant slope, and we apply the limit operator. We are now officially asking, what value does the slope of the secant line approach, asterisk, as h approaches 0 asterisk? When we take this limit, we are no longer calculating the slope of a secant line. We have found the exact slope of the tangent line at point P. This value has a special name and notation. It is the asterisk derivative asterisk of the function f at the point x, and we write it as f(x), f prime of x. This is it. This is the formal definition of the derivative. This single expression is one of the most important foundations of all of calculus. It is the machine that takes a function, f(x), and gives us a new function, f(x), that describes the instantaneous rate of change, the slope of the tangent line, at every single point on the original function. We have successfully bridged the gap from an intuitive idea of a tangent line to a precise, powerful mathematical definition. In the next scene, we'll put this powerful new machine to work. We'll take this very definition and apply it to our function, y equals x2, to finally calculate its derivative and find the slope at any point we wish. In the previous scene, we established the formal, rigorous definition of the derivative. It might have seemed a bit abstract, a bit theoretical. Now, in scene 6, we're going to make it concrete. We're going to roll up our sleeves and use that definition to find the derivative of a function you know very well. The simple parabola, f of x equals x squared. There it is on the right. Our goal is to find a general formula for the slope of the tangent line at asterisk any asterisk point x on this curve. Here's our tool, the limit definition. F prime of x is the limit as h approaches 0 of the slope of that secant line. Our first step is to substitute our specific function, x squared, into this general formula. The term f(x plus h) becomes x plus h squared, and f(x) simply becomes x squared. Now the real work begins. Right now, if we tried to plug in h equals 0, we'd get 0 in the denominator, which is undefined. Our entire goal with the algebra that follows is to manipulate this expression so we can cancel out that h in the denominator. First, let's expand the x plus h, two-term, to see all the individual pieces. This gives us x squared plus 2xh plus h squared. Excellent. Notice that we now have an x squared at the beginning and a minus x squared at the end. These two terms cancel each other out perfectly, simplifying our numerator. Now, look at what's left in the numerator, 2xh plus h squared. Do you see the common factor? Both terms contain at least one h. Let's factor that h out. This leaves us with h multiplied by the quantity 2x plus h. And this is the magic moment. This is what all that algebra was for. We now have an h in the numerator and an h in the denominator. Since h is approaching 0, but is not asterisk equal asterisk to 0, we are allowed to cancel them out. This resolves our divide by 0 problem. We're left with the limit as h approaches 0 of just 2x plus h. And now, finally, we can let h go to 0. The h term vanishes, and we have our answer. The derivative of x squared is simply 2x. This is a profound result. It's a new function, f prime of x equals 2x, that tells us the slope of the original function, f of x equals x squared, for any value of x we choose. So, what does this actually look like? Let's connect our new formula back to the graph. Let's pick a point, say, where x equals 1. According to our formula, the slope of the tangent line here should be 2 times 1, which is 2. And look, the slope of our tangent line is exactly 2. Now, watch what happens as I move the point to where x equals 2. The line gets steeper. Our formula predicts the slope should be 2 times 2, which is 4. And indeed, the slope is exactly 4. It works for negative values too. At x equals -1, the formula predicts a slope of 2 times -1, which is -2. The line slopes downwards, and its slope is precisely -2. And what about at the very bottom, at the vertex where x equals 0? The formula says the slope should be 2 times 0, which is 0. And that's exactly what we see. A perfectly flat, horizontal tangent line with a slope of 0. This is the power of the derivative. We've moved from a cumbersome limit definition to a simple, elegant formula, f x equals 2x, that perfectly describes the instantaneous rate of change of our parabola at every single point. In the previous part, we went through the entire rigorous limit definition to find the derivative of x squared. And while that process is crucial for understanding why a derivative works, it was a lot of algebraic effort for a relatively simple function. It begs the question, is there a faster way? Calculus is not about making things harder, it's about building powerful tools. So let's be detectives for a moment. Let's look at the results for a few simple power functions and see if a pattern emerges. We already know the derivative of x squared is 2x. For clarity, let's write that as 2x to the power of 1. Now, if you were to go through that same limit process for x cubed, you would find that its derivative is 3x squared. And for x to the fourth, you'd get 4x cubed. Now, pause and look closely. Do you see the relationship? Let's break it down with the x cubed example. Notice the original exponent, this 3. Where does it appear in the derivative? Right here as the new coefficient in front of the x. And what about the new exponent, this 2? Well, it's exactly 1 less than the original exponent. 3 minus 1 is 2. The old exponent comes down to the front, and the new exponent is 1 less than the old. This beautiful pattern holds for all of them, and it's not a coincidence. It's a fundamental shortcut in calculus known as the power rule. Formally, it looks like this. The derivative with respect to x of x raised to some power n is equal to n times x to the power of n minus 1. Let's watch that in action. The rule tells us to take the original exponent, n, and bring it down in front to become the new coefficient. Then, for our new exponent, we just take the original exponent and subtract 1. That's it. That's the entire rule. It's simple, elegant, and incredibly powerful. Its real power is revealed when we apply it to more complex functions, like this polynomial. Using the limit definition on this would be a nightmare. But with the power rule, and the fact that we can differentiate term by term, it becomes straightforward. Let's start. First term, 7x to the fifth. We apply the rule. The exponent 5 comes down and multiplies the existing coefficient 7. 5 times 7 is 35. The new exponent is the old one, 5 minus 1, which is 4, so the derivative is 35x to the fourth. Simple. Next term, minus 4x cubed. The exponent 3 comes down and multiplies the minus 4. 3 times minus 4 is minus 12. The new exponent is 3 minus 1, which is 2, so we get minus 12x squared. Now for the plus 2x term. This can be tricky, but just remember that x is really x to the power of 1. So the exponent 1 comes down and multiplies the 2. 1 times 2 is 2. The new exponent is 1 minus 1, which is 0. And what is anything to the power of 0? It's 1. So we have 2 times 1, which is just 2. So the derivative of 2x is simply 2. This makes sense. The line y equals 2x has a constant slope of 2 everywhere. Finally, the constant term, minus 10. Think about the graph of y equals 10. It's a flat, horizontal line. What is its slope? What is its rate of change? It's 0, it never changes. The derivative of any constant is always 0. So it contributes nothing to our derivative. And there we have it. In a few simple steps, we found the derivative of that entire polynomial. What took pages of algebra with the limit definition can now be done in seconds. This is the essence of learning calculus, mastering these powerful rules built upon those first principles to solve complex problems with elegance and efficiency. And that gives us the precise slope at that one specific point. But this raises a fascinating question. The function has a slope at every point. What if we could calculate the slope not just at one point but at all of them and then plot those values? What would that look like? In this scene, let's run that exact experiment. We'll set up 2 graphs. On top, we'll place our function. Let's use f of x equals sine of x. Below it, we have an empty set of axes. This bottom graph will be our canvas for plotting the slope of the top graph. We'll call it f prime of x, the derivative function. Let's start at the beginning, where x equals 0. Here, the sine curve is rising. If we draw the tangent line at this exact point, we see its slope is exactly 1. It's at its steepest positive incline. So on our derivative graph below, at x equals 0, we plot the value of that slope. 1. Okay, let's move to our first peak at x equals pi over 2. At the very crest of a wave, the function is momentarily flat before it starts to go down. Logically, the tangent line here must be horizontal, and a horizontal line has a slope of 0. So, down on our f' graph, at x equals pi over 2, we plot the value 0. Now, let's continue to x equals pi. Here, the function is decreasing, and just like at x equals 0, it's at its steepest point, but this time in the negative direction. The tangent line has a slope of -1, and so we plot -1 on our derivative graph. Let's do one more key point for good measure. At the bottom of the trough, at x equals 3 pi over 2, we're at another flat spot. The tangent is horizontal again, and its slope is 0, so we plot another 0 on our derivative graph. Now, take a step back and look at the points we've plotted below. A pattern is starting to emerge. We've only tested 4 points, but we could do this for every single point in between. The process is always the same. Find the slope on the top graph and plot that value on the bottom graph. Instead of doing that by hand, let's use the power of animation to do it for us. Watch closely. We'll sweep a point across our sine function, and as we do, we'll trace out the value of its slope on the graph below. Look at that. The collection of all possible slope values forms its own, beautiful, continuous function. This is the derivative function of sine. For any x you pick, the height of this new yellow curve tells you the instantaneous rate of change of the original blue curve at that exact x. Now, does this yellow curve look familiar? If you've studied trigonometry, it probably does. This is the graph of the cosine function. Let's overlay the actual graph of cosine to confirm. It's a perfect match. What we have just discovered visually is one of the most fundamental results in all of calculus. The derivative of sine of x is cosine of x. The derivative isn't just a single number. It's a completely new function that describes the rate of change of the original. Understanding this relationship between a function and its derivative is the key that unlocks our ability to analyze everything from planetary motion to economic models. In our journey through calculus so far, we've thoroughly explored and mastered the first great problem, the problem of slopes, which led us to the derivative. Now, in Scene 9, it's time to return to the second great problem, the one we introduced at the very beginning. The challenge of finding the area under an arbitrary curve. This area problem seems simple, but for most curves, there's no straightforward geometric formula. To build a method that works for any curve, let's start with a function we can actually solve with tools we already know. Let's consider the simple function, y equals x, and try to find the area under it from x equals 0 to x equals 4. Because this is just a straight line, the area we're interested in forms a perfect triangle. And for a triangle, we can use simple geometry. The area is 1/2 times the base times the height. In our case, the base is 4 units long, and the height, which is the value of the function at x equals 4, is also 4. So the area is 1/2 of 4 times 4, which gives us an exact area of 8. Okay, that was easy. But what if the curve wasn't a straight line? We need a more general strategy. Let's try to find this same area of 8, but this time using a method of approximation. The idea is to fill the area with shapes whose areas are very easy to calculate. Rectangles. We'll start by dividing our interval from 0 to 4 into 4 equal pieces and drawing a rectangle for each piece. Using 4 rectangles, the total area comes out to be 6, 0. As you can see, it's not a very good approximation. The gaps above the rectangles represent the area we've missed. The result, 6, is quite a bit less than the true area of 8. So, how can we get a better estimate? The logical next step is to use more, and therefore narrower, rectangles. Let's double the number from 4 to 8. Watch what happens to both the graph and our table. The gaps get smaller, and our approximate area increases to 7, 0. That's much closer to the true area of 8. We're on the right track. Let's double it again to 16 rectangles. Now the approximation is 7, 5. Notice the clear pattern here. As the number of rectangles increases, our approximate area gets closer and closer to the true area of 8. This should feel familiar. We're witnessing the concept of a limit in action. This leads us to the most important question of all. Our approximation gets better with more rectangles, but it's still just an approximation. To get the exact area, to eliminate every last bit of error, what do we need to do? The answer is the conceptual leap that opens the door to integral calculus. We need to let the number of rectangles go to infinity and their width shrink to 0. This process of summing up an infinite number of infinitesimally thin things is precisely what the integral is designed to do, and it's what we will explore next. In our exploration of integrals so far, we've focused on finding the area between two fixed asterisk points from A to B. The result has always been a single static number. But calculus is the study of change, so it's natural to ask, what happens if we let one of those boundaries move? This leads us to a powerful and profound idea. Instead of a static area, let's define an **area function **, which we'll call capital A of x. This function measures the accumulated area under a curve, f of t, starting from a fixed point, like 0, up to a variable endpoint, x. To understand this, we'll use two graphs. On the left, we'll plot our original function, which we can think of as a rate of accumulation. On the right, we will build a new graph for our area function, A of x, which represents the accumulated total. Let's begin with the simplest possible rate function, a constant value. Let's say f of t is equal to 2. This could represent moving at a constant speed of 2 meters per second, or water flowing into a tank at a constant rate of 2 liters per minute. Now, let's watch what happens as we let x, our endpoint, sweep from left to right. On the left, the shaded area grows. Since the height is a constant 2, the area is simply the base x times the height 2. On the right, for every value of x, we plot a new point. The x-coordinate of this point is our variable, x, and its y-coordinate is the total blue area we've accumulated on the left. When x is 1, the area is 2. When x is 2, the area is 4. When x is 3, the area is 6. The relationship is clear. The accumulated area is always 2 times x. The graph being traced on the right is a straight line. So, for the rate function ft equals 2, the area function is x equals 2x. A constant rate of accumulation leads to a linear or steadily growing total. That was straightforward. But the real power of this idea becomes apparent when our rate of accumulation is not constant. Let's reset and try a new function. Let's look at the rate function f of t equals t. Here, the rate of accumulation is itself increasing. The further we go, the faster we accumulate more area. Let's run our process again. This time, the shape of our accumulated area is a triangle. We know the area of a triangle is 1/2 base times height. In our diagram, the base is the distance from 0 to x, which is just x. The height of the triangle at any point is given by the function itself, so the height is f(x), which is also x. So the area is 1/2 times x, that's 1/2 x squared. And look at the graph being traced on the right. It's no longer a straight line. It's curving upwards, accelerating. It's a parabola. This curve is the graph of our new area function. For the rate function ft equals t, the total accumulated area is given by ax equals 1/2 x squared. Let's pause on this result, because this is incredibly important. We started with a rate function, ft equals t, and we discovered that its area accumulation function is x equals 1/2 x squared. Think back to our work on derivatives. What is the derivative of 1/2 x squared? It's x. What was the derivative of 2x from our first example? It's 2. It seems that the original rate function, f, is the derivative of the area function, a, or, put another way, the area function a is the antiderivative of the rate function f. This connection between finding an area and reversing differentiation is not a coincidence. It is the single most important idea in all of calculus, and it's what we will formalize in Scene 12, as we introduce the fundamental theorem of calculus. In our journey so far, we've established a powerful idea, that the accumulated area under a function can itself be thought of as a new function. We called it of x, the area SOFAR function. It's the total area under our curve, f of t, starting from some fixed point a and sweeping all the way to a variable endpoint, x. Formally, we wrote it as an integral. Now, in scene 12, we ask the pivotal question of calculus. If a of x is a function just like any other, it must have a rate of change. It must have a derivative. So, what is the derivative of the area function? What is a prime of x? To find the rate of change at x, we need to do what we always do with derivatives. We need to nudge our input x by a tiny amount, which we'll call h, and see how much the function's output changes. So let's zoom in right here, at the edge of our area. We'll introduce a new point, x plus h. This creates a new, thin sliver of area. This sliver is the change in our area function. It's the new area of x plus h minus the old area of x. Now, how can we calculate the size of this sliver? Look at it closely. It's not quite a rectangle because its top edge is curved, but if h is very, very small, that curve is almost a flat line. This sliver is approximately a simple rectangle. And what are the dimensions of this approximating rectangle? Well, its width is clearly h, and its height, it's the value of the function right at x. It's f of x. So the area of this sliver is approximately f of x times h. This is the crucial insight. We now have an expression for the change in area. Let's rearrange this. If we divide both sides by h, we get the change in area per unit of change in x. Look at what we have on the left. This expression should be incredibly familiar. It's the difference quotient for the function a. It's the very definition of the derivative, except for one thing, the limit. To make this a true derivative, we must take the limit as that little width h shrinks to 0. And as h approaches 0, the error in our rectangle approximation vanishes completely. The approximation is no longer an approximation. It becomes an exact equality. And now we see it. The limit of the difference quotient is, by definition, the derivative, a prime of x. The rate of change of the area function is just the original function itself. Differentiating the process of integration gets you right back where you started. This is an absolutely profound result. Let's clear everything away and state it formally. This relationship is the first part of the fundamental theorem of calculus. It states that the derivative with respect to x of the integral from a to x of f of t is simply f of x, the two great pillars of calculus. The derivative, which measures the rate of change, and the integral, which measures accumulated quantity, are perfect inverses of each other. This is the bridge that connects the entire subject. In the next part, we'll see how this incredible connection allows us to actually compute definite integrals with astonishing ease. In our last discussion, we arrived at a truly profound conclusion. The derivative of the area function, ax, is the original function fx itself. This single equation, the first part of the fundamental theorem of calculus, forms a deep and surprising bridge between the world of derivatives and the world of integrals. Now, in scene 13, we will cross that bridge to uncover the second part of the theorem, the part that gives us a stunningly practical method for calculating definite integrals. Let's start by thinking about what x equals fx really means. It means that a x is a function whose derivative is fx. In calculus, we have a special name for this. We call such a function an antiderivative of fx. So let's say we find one such antiderivative. We'll call it capital Fx. Its derivative, fx, is fx. But here's a critical question. Is this the only function that has this property? Think about what happens when you take the derivative of a constant. It's 0. This means that if fx is an antiderivative of fx, then so is fx plus 3 or fx10, or in general, any function of the form fx plus a constant c. Visually, this family of antiderivatives are all just vertical shifts of one another. They have the exact same shape. And if they have the same shape, they must have the same slope at any given value of x. Watch as we move along the x-axis. The tangent lines for all three functions are always perfectly parallel. Their slopes, their derivatives, are identical. They are all fx, so our area function, ax, since its derivative is also fx, must belong to this family. It must be equal to our chosen antiderivative fx plus some specific, yet-to-be-determined constant, c. This is the crucial link. The area is an antiderivative. Our entire goal now is to figure out the value of this specific constant, c. To find c, we need to use something we know for sure about the area function. Let's think about its starting point. The function ax measures the area starting from a. So, what is the value of the area function at the starting point, a? What is a? It's the integral from a to a, which is the area of a line with no width. That area is, of course, 0. This is the key that unlocks everything. We have a known value. a equals 0. Let's plug x equals it into our equation. And since we know a is 0, a simple rearrangement gives us the value of c. There it is. The constant of integration for our specific area function is the negative of the antiderivative f evaluated at the starting point, a. Now, we just substitute this expression for c back into our main equation for a x. This tells us the area from a to any point x. But we wanted the total area under the curve from a all the way to b. That's just ab. So we evaluate our new expression at x equals b. Look at what we have. The total accumulated area, ab, which is the definite integral we've been trying to find, is simply the value of the antiderivative at the endpoint, b, minus its value at the start point, a. Let's put this all together. ab is just our notation for the definite integral from a to b, so we can state our final, incredible result. The definite integral of a function f, x from a to b is equal to its antiderivative, f, evaluated at b, minus the antiderivative evaluated at a. This is the second fundamental theorem of calculus, also known as the evaluation theorem. It's one of the most important and powerful tools in all of mathematics. It tells us that to find the total area under a curve, we don't need to sum up millions of tiny rectangles. We just need to find one antiderivative, any antiderivative, since the c's would cancel out, and evaluate it at 2 points. This is the result that turns the difficult problem of integration into a practical, solvable procedure. And so, after this long journey, we arrive at the summit. We began this exploration with 2 problems that, on the surface, seem to have nothing to do with each other. The first was the tangent problem. How do we find the instantaneous rate of change of a function at a single point? The second was the area problem. How do we find the total area under a curve over an interval? For the entire first part of our journey, we treated them as separate domains. On one side, we had the world of derivatives, and on the other, the world of integrals. Let's visualize this. Imagine we have a differentiation machine. We can feed any smooth function into it, like our familiar friend, the parabola f(x) equals x2, when we ask this machine to do its work. To apply the principles of the limit to find the slope at every single point, it gives us a brand new function, the slope function. The output is the derivative, f(x), which, for our parabola, is the line 2x. This new function tells us the instantaneous rate of change of our original function at any value of x. This solved the tangent problem. Now, what about the other side of our story? Suppose we take this rate function, this derivative, and feed it into our integration machine. This machine was built to solve the area problem. It works by accumulating an infinite number of infinitesimally small pieces, a process also defined by the limit. When we ask it to find the net accumulation of this rate of change, what do you think comes out? Magically, we get our original function back. The integration process has perfectly undone the differentiation process. It gives us the net change function, which is precisely the function we started with. This is the central, breathtaking revelation of calculus. These 2 operations, born from 2 seemingly unrelated geometric questions, are perfect inverses. They are 2 sides of the same coin. Finding the rate of change and accumulating that change are processes that cancel each other out. One builds up what the other breaks down. This profound connection, this beautiful symmetry, is what gives calculus its immense power. It links the instantaneous to the total. And this relationship isn't just a neat visual trick. It is a rigorous mathematical truth, formally stated in what is, without exaggeration, one of the most important theorems in all of mathematics. It is called the fundamental theorem of calculus. The theorem has 2 parts. The first part tells us that if you integrate a function f and then differentiate the result, you get the original function f back. The derivative of an integral is the original function. The second part tells us how to use this inverse relationship to get a concrete answer. It says that to find the total accumulation, the definite integral, of a rate function from point A to point B, you don't need to sum up infinite rectangles. You simply need to find the original function f, the antiderivative, and evaluate the difference f b minus f a. This is it. This is the bridge that connects the two great continents of calculus. It's the engine that powers physics, engineering, economics, and so much of our modern understanding of the world. It is the beautiful, powerful, and fundamental idea that a process of infinite summing can be undone by a process of finding a slope. Thank you for joining me on this journey.